Welcome to your first Algebra 2 video lesson. We've been studying about logarithms, and now I would like to take a few minutes to talk about a few properties of logarithms. So first, let's take a look at the first box. It says, let's explore some cool facts about logarithms. Evaluate log base 3 of 3 plus log base 3 of 3 plus log base 3 of 3. The first thing we have to do is figure out what log base 3 of 3 is. So based on our introductory lesson on logarithms, log base 3 of 3, we said, okay, we're gonna set this equal to x, and then we're going to use our flip technique to turn this back into an exponential function. So this means 3 to the x power equals 3. So what would x have to be? X would have to equal 1. So think about that for any expression, say log base 5 of 5. Log base 5 of 5 would say 5 to the x equals 5. Therefore, x would have to be 1. It's true in all cases. Log base 10 of 10 is 1. Log base 7 of 7 is 1. So log base 3 of 3 is 1. So we have 1 plus, and then again we have another log base 3 of 3, so that's 1. And another log base 3 of 3 is 1. So if I were to evaluate this expression, it would be equivalent to 3. Now let's look at the second expression we have down here. Evaluate log base 3 of 3 times 3 times 3. Okay, well, we know that we can go ahead and multiply 3 times 3 times 3. So that we would end up with log base 3 of 27. Okay, using your flip technique to turn this into an exponential function, we realize that log base 3 of 27 would also equal 3. So these two expressions that we have here on our screen are equivalent. Log base 3 of 3 plus log base 3 of 3 is equivalent to log base 3 of 3 times 3 times 3. Take a look at what we've done here. We've taken the arguments. Now remember, the arguments are what are inside our logarithm. And instead of having 3 separate arguments, we took these 3's and we brought them together under one logarithm where we multiplied the 3's. Okay? This is called condensing the logarithms. We took 3 logarithms and we condensed them into one. If you remember correctly, what happens in exponential functions when we multiply two things with the same bases? What do we do with the exponents? We add the exponents. Okay, remember the logarithms are the inverse functions of the exponentials. In logarithms, when we go ahead and add logarithms with the same bases, we can actually bring them together and multiply the arguments. Okay, let's go down here and scroll down a little bit and take a look at the next box. We have log base 3 of 27 minus log base 3 of 9. What we first have to do is evaluate log base 3 of 27 and log base 3 of 9. Okay, from the previous problem, we have already evaluated what log base 3 of 27 is. We decided that that was 3. Because 3 to the third is 27. Using the same flip technique, let's go ahead and evaluate Let's go ahead and evaluate what log base 3 of 9 would be. So take a minute and evaluate what log base 3 of 9 would be. Log base 3 of 9 means 3 to the x is 9, therefore x would have to be 2. So what we end up with is 3 minus 2, which would equal 1. Now let's evaluate this next expression. Okay, we have log base 3 of 27 divided by 9. So let's go ahead and divide the 27 by 9 to get log base 3 of 3. And of course, based on our previous example, log base 3 of 3 is 1. So once again, we have two equivalent fractions. Two equivalent expressions. So if you take a look at this, log base 3 of 27 minus log base 3 of 9 is equivalent to log base 3 of 27 divided by 9. Let's take a look at what we did. We took our two arguments, the 27 and the 9, and we divided them. So when we had two logarithms that were subtracted, we actually brought them together under one logarithm where we divided the arguments. Okay, once again, think back to exponentials. In exponentials, if we are dividing two expressions that have the same base, what do we do with the exponents? We subtract them. Remembering that logarithms are the inverse of exponentials, if we have two logarithms that we're subtracting, we can go ahead and divide the arguments. Okay, let's scroll down just here a little bit more and take a look at this third expression. This one's not quite as intuitive as the others, but let's go ahead and evaluate it. First we have 2, which represents this first 2, and then we have log base 2 of 4. So using your flip technique, changing the logarithm to an exponential, what would log base 2 of 4 equal? So giving us the equivalent exponential, it would be 2. Whoops, sorry about that. There we go. It would be 2 to the x equals 4. So x would equal 2. So what we have here is 2 times 2, which equals 4. Okay, now let's go ahead and evaluate the next expression. What we have here is we have log base 2 of 4 squared. So let's go ahead and replace 4 squared with its equivalent, which is 16. And using our flip technique, once again, I'll give you guys a second to do that. Flip it over, change it to an exponential, and decide what x would be. What would the exponent be? 2 to what power is 16? And the answer is 4. Once again, we have two equivalent expressions. We're saying that 2 times the log base 2 of 4 is equivalent to the log base 2 of 4 squared. So let's go ahead and try to take a minute and look at the difference between these two equations. And the difference lies here. This 2 that's on the exponent here, we can actually bring down in front of the exponent, in front of the logarithm as a multiplication. Same thing working backwards with the top one. If the 2's out front, we can actually bring it back up on top of the argument as the exponent of the argument. Those two expressions are equivalent. So I like to term this the exponent that fell. Sometimes it's going to help us to take an exponent and drop it in front of the logarithm, and sometimes it's going to help us to actually go in reverse, where we see the exponent that may have dropped in front of the logarithm and put it back up in, as the exponent of the argument. Okay, so scrolling down a little bit more here, I've kind of summarized what we did. You just discovered the three properties of logarithms. And once again in review, with exponents, when we multiply terms with the same base, we add the exponents. With logarithms, when we add several logarithms with the same base, we multiply the arguments. As with exponents, when we divide terms with the same base, we subtract the exponents. With logarithms, when we subtract two logarithms with the same base, we divide the arguments. And the last one actually falls from a little bit lengthier explanation following the first law of logarithms. If we have the same number, if we have a number times a logarithm, it becomes the exponent of the argument. Now we can use these properties in two ways. We can use them to expand logarithms that are already condensed into one logarithm, or we can condense several logarithms into a single logarithm, and both have their own applications. So let's look here at our first set of examples. If I look at our first set of examples, the directions are: express each logarithm as the sum or difference of logarithms with no exponents. Okay, so we're going to start to apply several of these properties, these three properties of logarithms that we've developed. Let's take a look at example number 1. I have the log base 2 of m times n. Do you see how m and n are multiplied here? Working the properties a little bit in reverse, we're actually going to expand this now into several logarithms. We're going to go ahead and separate this. Remember, just like in exponents, when we multiply, we add exponents. Very similar here. Because these two arguments are multiplied, I can expand them into their individual logarithms that are added. So this actually expands into the log base 2 of m times the log base 2 of n. And that's actually all they're asking us for in this problem, is to go ahead and write this as the sum or difference of logarithms with no exponents. So what we have here is we have two logarithms that are added together, and notice neither of our two arguments has an exponent. So we've actually done what the directions have asked of us. Let's go ahead and take a look at the second one now. We have the log base 2 of m divided by n. Okay, think about it for a minute. Just like exponents, when we have exponentials and we're dividing them with the same base, we go ahead and subtract the exponents. Working very similarly here with a logarithm, if I want to expand these into two logarithms, I'm going to say the log base 2 of m minus the log base 2 of n. And when you're doing the subtraction, it's always the numerator first. So you'll do the log base 2 of the numerator minus the log base 2 of the denominator. And again, we've expanded into the sum or difference with no exponents. Okay, let's take a look at example number 3 now. Think about our PEMDAS. With PEMDAS, we know we take care of parentheses and then exponents. Same thing applies here. Of course, I have no parentheses in example number 3, but I do have an exponent. And remember, the directions are to express each logarithm as the sum or difference of logarithms with no exponents. So based on that third property of logarithms we talked about, this exponent can actually come and drop right down in front of our logarithm. So it's 4, and it becomes a multiplication now, times the log base 2 of m. And again, we don't have any other thing in our argument other than m. M is now the only thing that's in our argument. So there's no expanding to be done. There's no multiplication or division within, there's no multiplication or division within the argument. Therefore, there's nothing to expand. And our argument does not have any exponents because we actually took that exponent of the 4 and dropped it down in front. So we've satisfied the requirement of express each logarithm with no exponents. Okay, now let's take a look at number 4. Log base 2 of the cube root of m squared n. Okay, now we're going to put it all together. In the first example, we only applied one property, and that was the sum. In the second example, we applied the difference property, and in the third example, we applied the exponent property. Now we have to apply several properties within one problem in order to expand this to be the sum or difference of logarithms with no exponents. So I'm just going to go ahead and scroll over here for a minute so that we have a little bit more room to write. So let's take a look at this. Just like we've done, and I spoke to you the other day about the 3 steps in solving some of these things. And one of the first ones was to change our radicals to exponents. That's a great way to make the problem a lot easier to work with. It's actually easier to work with exponents than it is to work with radicals. So what I'm going to do is I'm going to go ahead and change the cube root to an exponent. So I'm going to add a set of parentheses here just to make things neat and clear and to understand that this exponent is going to apply to this total argument of m squared n. Whoops, sorry about that writing there. So what exponent would I use? Remember, top number is the exponent, bottom number is the root. The exponent's actually a 1 here, and the root's a 3. So what I've done is I've changed that that cube root to a 1/3 exponent. Okay, now remember PEMDAS, going to take care of the exponent first. So the first thing I'm going to do is go ahead and drop this 1/3 way down here into the front of my logarithm. So what I have now is 1/3. And now I'm just going to use a square bracket because I have to understand that this 1/3 was the exponent on the entire argument. So it's going to actually apply as a multiplication to our entire problem. Now, taking a minute to look at this argument, I'm going to apply something. I'm going to apply 2 properties at once to save ourselves a little bit of time. Do you see how the m squared and the n are multiplied? Okay, remember, multiplication means addition here. So I'm going to separate these into 2 logarithms. So I'm going to do log base 2 of m squared plus log base 2 of n. Okay, because they were multiplied, I separated them out into their individual logarithms where they're added. Okay, and now you're almost done. Does one of our arguments still have an exponent? The m squared still has that exponent of a 2. We have to go ahead and drop that exponent down in front. Now, since this squared is only on the m, it only applies to that logarithm. So I'm going to take the 2 and I'm going to drop it down right in front of that log. I don't want to drop it in front of the whole thing, otherwise it'd apply to the log base 2 of n, and it doesn't. So let's go ahead and rewrite our problem, and we'll be at our final expansion here. We have 1/3 square bracket. You could have used round brackets. I just think square brackets are neater. 2 log base 2 of m plus log base 2 of n. And we've satisfied our requirement to expand it into the sum or difference of logs, and there are no exponents on our arguments. Okay, remember, if you have any questions, go ahead and write them down at the bottom of your notes, and we'll address those questions in class. Okay, scrolling back over a little bit, I'm going to show you a couple of examples where these are somewhat helpful. Okay, so let's look here. Okay, so we have to pretend at this point that we have no calculators. Okay, and all we know in the world is that the log base 10 of 9 is 0.95 and the log base 10 of 2 is 0.30. They want us to find the following. And again, I gave you a little hint there. Remember that the log base 10 of 10 is 1. So we want to evaluate what in the world the log base 10 of 9/2 would be without the use of a calculator. Now, just to let you know, these numbers of 0.95, these numbers here of 0.95 and 0.30 are rounded. Okay, they're just decimal approximations of what actually the log base 10 of 9 is. Because if you think closely, the log base 10 of 9 would mean 10 to what power is 9? Okay, it's not a pretty number. So we just went ahead and calculated that out and rounded it. So now we're going to use our techniques of expansion here. Do you see how these two arguments are divided? Okay, remembering division means we're going to subtract the logarithms. So I'm going to go ahead and expand this out using our techniques of expansion. The log base, oops, I'm writing log base 2 because we were just doing log base 2. So log base 10 of 9 minus log base 10 of 2. Okay, now we know the decimal approximations of these two. In the directions, they told us that the log base 10 of 9 was 0.95 minus the log base 10 of 2 is 0.30. So then we go ahead and subtract those two, and we get 0.65. Okay, so there's an example where our expansion really helps us evaluate some of these expressions. So now let's take a look at number 6. Log base 10 of 900. Okay, this one's going to be a little bit tricky. We're going to have to use a little bit of work. What we want to do is we want to go ahead and try to express 900 in terms of 9, 2, and 10. We want to use multiplication and exponents with 9, 2, and 10, a combination of one of them, two of them, all three of them, in order to obtain 900. So I'm sure most of you can think about this fairly quickly and recognize that log base 10 of 900 can be written as the log base 10 of 9 times 100. Okay, so I've successfully worked my 9 in there, but I don't know what the log base 10 of 100 is. So now I have to rewrite 100 in terms of 10 using multiplication or exponents. So at this point, you can make it 10 times 10, or you can make it 10 squared. 10 squared is certainly 100. And I've successfully written 900 in terms of 9 and 10. I didn't need to use the 2 here. So I'm just going to scroll down a little bit so I have a little bit more room to write. Now we're going to use our expansion here. We're going to expand these out. These two right here, the 10 and the 9, are multiplied. So I'm going to go ahead and expand them out to be addition. So it's going to be the log base 10 of 9 plus, and I'm going to go ahead and do the log base 10 of 10 squared. But to save ourselves a little bit of time, instead of having the squared up here, I'm just going to go ahead and drop it down in front right now. I'm going to go ahead and drop that 2 down in front so we no longer have that 2 up there. Now all you have to do is replace these with their decimal equivalents. So I now know that the log base 10 of 9 is 0.95 because they told me that in the directions. Plus 2 times, and the log base 10 of 10, I told you in the directions, and we also went over it at the beginning, the log base 10 of 10 is 1. So calculating this out, I have 0.95 plus 2 is 2.95. Okay, let's look at our last example on expansion, and then we'll work on some contraction of these. Number 7. Again, that theme that constantly comes around is that we need to change our radicals to exponents. Okay, we need to change our radicals to exponents. It's so much easier to work with them in exponential form than radical form. So what I would have, I'm going to add some parentheses because I want to make sure I understand that the exponent applies to the 2/9. So I have the log base 10 of 2/9 to the 1/3 power. And this is one of my favorite properties because it actually gets rid of all your exponents together altogether by taking that 1/3 and dropping it down in front. So I have 1/3, okay, very similar to the example we just did above this. And now, since these two arguments are this argument is a division, I'm going to go ahead and expand them into their own logarithms where they're subtracted. So log base 10 of 2 minus log base 10 of 9. Okay, remembering that the numerator comes first in the subtraction. Then we go ahead and replace everything with its decimal equivalent. So what I would have is I would have, pick up my pen here, 1/3, hope I'm not going off the screen, I think I am a little bit, 1/3 log base 10 of 2, which is 0.30. Let me scroll down a little bit here so we kind of have a little bit more room to write. Log base 10 of 2 is 0.30 minus 0.95, which was the log base 10 of 9, its decimal equivalent, which would go ahead and give me 1/3, and then 0.30 minus 0.95 is negative 0.65. Okay? Okay, remember, whoops, remember we're not going to have fractophobia here. We're going to make sure that we know how to work with our decimals and our fractions. Okay, so this would be, again, I'm going to scroll down just a little bit so I have a little bit more room to write. This would be negative 0.65 over 3. Now, of course, we don't want to leave decimals within fractions. Okay, so there's a couple of ways you can go ahead and get rid of the decimals. You can simply multiply the top and bottom by 100. So you get negative 65 over 300. Whoop. And then go ahead and reduce that fraction. If you divide them both by 5, I believe it would be negative 13 over 60. Negative 13 over 60. And that is reduced form. Okay, we're going to take a break here. And I'm going to go ahead and put the second half on another second video as to not make the videos too long. This would be a great time for you to take a break also.